Hello. Saddleback College Robotics is proud to present our 5th generation rover, Helios. Our team is divided into 5 subsystems: chassis, drive, arm, science, and autonomy. We constructed our chassis out of welded 6063 aluminum tubing and a riveted floor pan, ensuring high strength and rigidity while maintaining a low weight. To reduce chances of brownout or communication loss, our rover is powered by 4 high energy density lithium-ion batteries with power split between a 48-volt battery powering computing electronics and 3 12-volt batteries connected in parallel, powering the drive, arm, and science systems. Additionally, each battery is paired with a battery management system. A custom PCB integrates both a hard and soft kill switch, which allows us to cut all power while keeping computing electronics online, or cut all power in case of an emergency.
Helios' 5 degree of freedom arm mounts 2 heavy-duty linear actuators on a fiberglass frame, making it strong, rigid, and lightweight. At the base is an azimuth turret whose hypocycloidal cage pinion and ring gear mechanism produce high torque with 0 backlash. The turret is modular and the payload is swapped between arm and science missions. Our lead screw end effector is mounted on a series of gear trains for precise positioning. It features textured neoprene grips to securely grasp various objects, and it houses both a small linear actuator for pressing buttons as well as a hex key for tightening screws. Each axis of the arm is controlled with closed-loop control for precise arm pose.
This year for our drive system, we have designed a custom control arm suspension with an adjustable pneumatic shock that can provide sufficient dampening over extreme terrain and even further reinforcement and movement across all mission operations. Our control arms are lightweight and modifiable, allowing Helios to fit within the size and weight requirements. 42 centimeter low pressure pneumatic tires are used to increase our ground contact patch to reinforce our rover with improved climbing capabilities. This is held together with a 3D printed bearing block and a clamshell hub. Each wheel is powered by 400 watt brushless DC motors using 80-to-1 planetary gearboxes, generating an overall output torque of 210 Newton meters. For our motor drivers, we're using dual motor controllers with 3-phase Hall effect sensor feedback and integrated PID loop controls capable of up to 120 amps of continuous current.
The science team has further developed our mission by improving sensitivity and efficiency. Our science package includes life detection via ATP chemical luminescence analysis, capable of detecting and quantifying ATP in soil samples even at extremely low concentrations. Samples are vacuumed into a light-sealed testing chamber mounted onto the rover for analysis. They are filtered into cuvettes containing a chemical solution, and luminescence is measured via a photomultiplier tube. Results are transmitted wirelessly back to the base station. The testing chamber also contains a sealable compartment where a sample can be stored and retrieved after the mission. With our enhanced UV fluorescence experiment, we can detect past life in soil and rock samples, specifically from mineral signatures and fossils. We will use an original science team-developed algorithm that examines RGB values pixel by pixel for spatial analysis of rock samples.
For this year, communication with the rover is achieved through Ubiquity's AirMax Rocket 2 AC Prism radio and Bullet AC IP67 on the 2.4 GHz radio band, which are optimized for non-line-of-sight communication and high-bandwidth data streams. The telecommunication system is run across a point-to-point network connection where control commands and analog signals from the base station interface are sent downstream while telemetry is sent upstream through RAP ROS2 nodes. The ROS2 interface enables the user to control motors, cameras, and status signal, as well as monitors, process indicators, and video feeds. To control the arm, we are using a virtual twin simulation of the arm, which is an implementation of inverse kinematics for positioning. A DualShock PS4 controller is also utilized for drive control, providing more freedom of movement and enabling manual drive over network.
All autonomy modules communicate onboard the rover via ROS2 nodes. Autonomous navigation is achieved using differential GNSS to accurately determine the rover's location. A GPS waypoint is then provided to guide the rover to a target location. We are using the magnetometer on the NavX IMU to orient the rover according to its calculated travel vector. We use the Z2i stereo camera as input for VSLAM. Additionally, we are leveraging the Nav2 library with inputs from VSLAM, LiDAR, GPS, and IMU and magnetometer for path planning, obstacle avoidance, and waypoint mapping. We are using Nav2 search algorithms for search route optimization, which includes Dijkstra's and A*STAR.
The OpenCV Aruco tag detection module will also help us in determining the accurate location of Aruco tags placed on signposts throughout the field.
If a tag is found, the rover will orient itself towards the tag and drive to a target distance from the tag. The Aruco tag detection is pre-calibrated for distance estimation prior to the mission. If a gateway is created by 2 Aruco tags, the rover will keep track of the distance of both Aruco tags and drive between the gateway.